Hello friends, welcome to my YouTube channel. My name is Prathmesh. Without wasting our time, let's begin. And if you like, please like, share, and subscribe.
Today, modern enterprise machine learning pipelines process millions of data points per second across highly distributed network nodes. This sheer velocity of information entirely outpaces traditional manual security interventions. To maintain control over these sprawling systems, the industry relies on rigorous standards, most notably the AI Risk Management Framework published by the National Institute of Standards and Technology. The NIST framework provides a comprehensive taxonomy of risk. It tells organizations exactly what vulnerabilities to look for, from data poisoning to model drift. But it stops short of explaining the precise technical mechanics of how to neutralize them. The first function of NIST, govern, establishes accountability through cross-functional committees. Legal, IT, and data science teams convene to set risk tolerances and draft ethical guidelines. However, a committee cannot directly patch a live system vulnerability. This creates a critical disconnect for ML SecOps practitioners on the ground. They are handed high-level legal and ethical mandates and left to figure out how to translate those documents into hard code and infrastructure controls. AI compliance cannot survive as a static policy document. Closing this gap requires a deployable systems architecture that forces abstract governance into continuous technical execution. Executing this mandate requires a centralized environment, which is the primary function of the Databricks Data Intelligence Platform. Within this platform, the Databricks AI Security Framework serves as the operational bridge connecting theoretical standards to deployed engineering. It takes the four core NIST functions, govern, map, measure, manage, and maps them directly against 62 technical risks across the platform. While governance sets the rules, the actual defense of an AI system happens downstream. We need to examine exactly how security teams execute the measure and manage functions across a live lifecycle. By linking these specific NIST requirements to hard engineering controls, the Databricks framework transforms a theoretical risk assessment into an automated defense system. Before security teams can measure a risk, they must map the specific technical terrain where that risk lives. In the Databricks architecture, this map begins with a single, non-negotiable foundation, Unity Catalog. This layer operates as the centralized security backbone. It forces all datasets, active models, and final AI outputs to pass through a single, unified access control checkpoint. Above this foundation, the framework structures the entire AI lifecycle into four primary operational pillars: data operations, model deployment, and platform management. Inside these pillars exist 12 distinct structural components, tracking the flow of information from raw data ingestion all the way to final model serving. Each component introduces specific vulnerabilities that require active control mechanisms. This 12-component model provides the structural granularity required to trace a risk from the platform level down to an individual operational node. This brings us directly to the NIST map function. This is the mandatory reconnaissance phase, executed before any active telemetry or mitigation begins. To catalog these vulnerabilities, Databricks provides specialized tools, starting with the AI Bill of Materials, or AI BOM. Security engineers use the AI BOM to document precise, mathematically verifiable data lineage. It links a currently deployed model artifact, tracing backward through the 12 components, to isolate the exact raw data sources used in its training. You cannot secure a dependency you do not know exists. The AI BOM establishes the definitive map of the organization's attack surface. With the terrain mapped, operations shift into the NIST measure phase, where risk severity is actively quantified within the model operations and deployment stages. The baseline for measurement relies on standard quantitative telemetry. Engineers track specific metrics over time to verify that the model maintains required thresholds for statistical fairness and outcome explainability. But standard IT vulnerability scanning falls short here. Traditional software checks network ports and code signatures. It cannot evaluate the behavior of a machine learning model processing complex, unpredictable human language. To uncover behavioral threats, teams deploy specialized red teaming. This subjects the model to rapid-fire malicious inputs, aggressively stress-testing its reaction to adversarial manipulation. The specific targets of this testing are unique to AI. Red teams intentionally deploy prompt injections to bypass instructions, or attempt model inversion attacks to extract sensitive training data from the output. Every interaction during the red teaming exercise is captured by platform telemetry. The severity of a successful prompt injection is instantly logged, and formal impact scores are dynamically calculated. These resulting scores do not sit in isolation. They are fed directly into risk assessment templates explicitly structured around the NIST reporting requirements. The measure function takes the vast unknown variables of AI behavior and refines them into quantified, prioritized security tickets ready for resolution. Passive measurement is only half the equation. The NIST manage function requires active architectural mitigation to resolve those tickets. The framework neutralizes the 62 identified risks by deploying hard technical controls directly into the vulnerabilities identified across the 12-component architecture. At the application layer, infrastructure controls like rate limiting are enforced at the API gateway. This throttles incoming requests to prevent denial of service attacks and compute resource exhaustion. At the delivery layer, active output filtering acts as a mesh. It intercepts the model's response payload, blocking toxic or hallucinatory outputs before they ever reach the end user. Down at the data layer, Unity Catalog executes mitigation by enforcing strict role-based access control, guaranteeing that unauthorized users cannot expose or modify sensitive model artifacts. By configuring these specific Databricks controls, the engineering team guarantees explicit line-item alignment with domestic regulatory standards, specifically the controls outlined in NIST 853. The operational scope also scales internationally. The exact same control mapping satisfies the mandates of the EU AI Act and ISO 42001. The manage function is the operational layer where abstract compliance mandates are converted into specific, auditable infrastructure controls. When fully executed, the enterprise AI environment operates as a continuous, self-reinforcing ecosystem. Security protocols are not bolted onto the end of a deployment pipeline right before launch. They are systemically integrated into the architecture from the moment raw data hits the catalog. The platform maintains its integrity through a continuous operational loop. Red teams constantly probe for any new vulnerabilities, telemetry captures the impact, and output filters automatically update to manage the threat. By mapping engineering realities to the 4 NIST functions, the framework provides a direct technical translation for legal governance standards set at the organizational level. The Databricks AI Security Framework ensures that risk management does not stall at the committee level. It takes the theoretical exercise of compliance and builds it into a fortified, deployable reality. Look at the sprawling, non-deterministic architecture of a modern large language model. We have a severe disconnect in enterprise AI right now. On one side, governance teams are writing high-level risk frameworks. On the other, engineering teams are deploying these chaotic, highly dynamic machine learning pipelines. The problem is that a static PDF document cannot intercept a real-time prompt injection attack. It certainly cannot detect a targeted data poisoning attempt buried in terabytes of training data. If compliance standards like the NIST AI Risk Management Framework or the EU AI Act are going to be effective, they have to be translated into programmatic infrastructural controls. The Databricks AI Security Framework, or DASF, is built exactly for this purpose. It provides a strict mathematical bridge between organizational governance and executing code. It achieves this by taking abstract concepts of risk and mapping them to 62 specific technical security controls applied across the entire AI pipeline. The enforcement mechanism for this is Unity Catalog, which acts as the centralized security backbone for the entire data intelligence platform. Modern AI security has become a deterministic infrastructure challenge. Before we can apply any of those security controls, we have to precisely define the topology of the AI attack surface. This diagram illustrates the 12 foundational components of an enterprise AI system. These nodes represent the technical journey from raw data ingestion to final model serving. We group these components into 4 major lifecycle stages: data operations, model deployment, and platform management. The highest probability of compromise occurs at the seams. Handoffs between these 4 distinct stages create operational vulnerabilities. To secure this architecture, compliance frameworks must be forced to map directly onto these specific physical nodes. This brings us to the 4 core functions of the NIST AI Risk Management Framework: govern, map, measure, and manage. A viable enterprise architecture must execute all 4 of these functions simultaneously, continuously, and across all 12 pipeline components. The execution starts with the map function. You cannot secure what you cannot see, making the inventory of all assets and their downstream dependencies the mandatory first step. The required artifact for this mapping process is an AI bill of materials, or AI BOM. Unity Catalog automatically generates this AI BOM by relentlessly tracking data lineage, tracing the flow from raw data tables into the feature store, and finally into the model registry. This lineage exposes the exact origin of context-specific risks. If an adversary executes a data poisoning attack, we trace that corrupted input directly to the deployed model. Because we have this exact lineage mapped, engineers can sever the connection. This isolates the corrupted dataset and neutralizes the threat before the model outputs malicious results. This visibility feeds directly into the govern function. Governance is entirely dependent on the accurate asset mapping we just performed. Cross-functional committees across legal, IT, and data science use this unified visibility to establish accountability and set strict risk tolerance guidelines. Maintaining a centralized AI BOM also enables rapid compliance mapping against external standards, like ISO 42001 or the EU AI Act. Unity Catalog turns passive, point-in-time compliance auditing into an automated, real-time lineage graph. Next is the measure function. We move from mapping what exists in the system to calculating its actual technical vulnerability. The primary method for detecting emerging AI-specific threats is through specialized red teaming assessments. Look at this visualization of model inversion. An attacker queries the model to reconstruct the sensitive, raw data it was trained on. It requires precise measurement to detect and prevent. The second major threat factor analyzed during this phase is prompt injection, where malicious inputs manipulate the model into bypassing its own safety constraints. To quantify these threats, the framework uses risk assessment templates structured directly around the NIST functions. This dashboard shows how abstract concepts are translated into quantitative impact scores. When simulated prompt injection attacks hit the deployment node, we capture the exact impact score based on the model's reaction. The measure function prevents risk from remaining a theoretical discussion. It forces vulnerability into hard, quantitative metrics prior to deployment. Finally, we reach the manage function. This is where measured risk dictates active technical enforcement. Returning to our complete AI lifecycle diagram, we can see where these deterministic controls are deployed. The entire pipeline is now enveloped by a unified security layer driven by Unity Catalog. Unity Catalog enforces centralized role-based access control across raw datasets, individual models, and specific AI outputs. At the serving layer, we implement technical controls like rate limiting. This immediately throttles incoming requests to prevent denial of service attacks against the model. We also deploy output filtering to mitigate risks. This analyzes and actively rejects malicious outgoing model responses before they reach the user. These are strict, configurable technical barriers built directly into the infrastructure. They are not optional guidelines left to developer discretion. These runtime controls complete the NIST feedback loop. They actively manage and mitigate the exact vulnerabilities that were mapped and measured in the preceding steps. The manage function establishes a strictly governed operational environment, ensuring model outputs are verified against measured risk. This brings us back to our opening dilemma. Here is the disconnect between a text-heavy risk policy and an active machine learning pipeline. Risk management frameworks are only as effective as the underlying architecture that enforces them. Unity Catalog and the Databricks AI Security Framework act as the central nervous system. They fuse abstract policy with concrete infrastructure. It creates a bidirectional flow. Infrastructure metrics continuously inform the policy layer, which automatically deploys strict controls back into the pipeline. We now have 62 technical controls explicitly and programmatically linked to the abstract functions of the NIST AI Risk Management Framework. By operationalizing this framework, enterprise architects build compliance directly into an active, impenetrable architectural defense.